It's been a site of human activity for 15,000 years. This land is the territory of the Huron-Wendat and Petun First Nations, the Seneca, and most recently, the Mississaugas of the Credit River. The territory was a subject of the Dish with One Spoon Wampum Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. Today, the meeting place of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in the community on this territory. So welcome to AstroTours. I'm Elisa, one of the co-directors, and this is a monthly organization. If this is your first time coming out, we run usually the first Thursday of every month with a talk and activities after the talk, and it's entirely run by the graduate students here at the University of Toronto, primarily in astronomy and astrophysics and also physics. So on your way in, we gave out feedback forms. We really value the feedback we get to help us improve our events. So after the talk, we have pencils if you don't have your own writing utensils to fill them out. And if the warm, good feeling of just doing something nice isn't incentive enough, we also have cookies if you hand in your feedback form. So tonight's talk is by Deborah Lockhorst. She is also the other co-director of AstroTours. If you've been to events so far in the last year, you've probably seen me up here. Deborah has been running a lot of other things behind the scenes, but tonight she's giving our talk. So she's from Victoria and did her bachelor's degree at the University of Victoria. In addition to all the astronomy stuff that she does here at the University of Toronto and also the Dunlap Institute, she enjoys hiking. She's also a phenomenal piano player. It's wonderful. And she'll be talking tonight about the Dragonfly Telescope, which is a really cool telescope that's being used to make really incredible discoveries. And is really just sort of, well, she'll tell you all about it, so I won't give it away. After the talk, we have planetarium shows. I believe we've given out all of the tickets, so those are 15 minutes. If you have tickets, you'll just show up at the planetarium meet point, and I'll talk more about it afterwards. So I'll save time for that. In principle, we do telescope observing, but I think it might be too cloudy for that, so we'll have an update at the end of the talk just to see if that's going on, but we still have other activities and demos for you. So with that, we'll get started, and let's all give Deborah a warm welcome.
Okay, is this on? Can you hear me? Good? All right, so as you heard, my name's Deborah, and I'll be talking today about discovering new galaxies with the Dragonfly Telescope. So, of course, the topic of this talk is focused on galaxies. So I think most of you, if not all of you, know what galaxies are and have seen pictures of them before, especially... Okay. Especially because we live in a galaxy ourselves, the Milky Way, which is a spiral galaxy. But just to give you a reminder, here's some pictures of galaxies. So this is a galaxy. This is a galaxy. This is a galaxy. It's a galaxy, 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 and that is also a galaxy. So they come in all shapes and sizes, and we give them a basic definition that they're collections of gas, dust, stars, and dark matter, which I'll get into later, which are all bound together by gravity. Does this work? Yes. Okay, so astronomers have roughly defined two basic types of galaxies. So one type is elliptical galaxies, and these are fairly featureless, smooth, spheroidal type of galaxies. And then the other main type of galaxies are spiral galaxies, like the Milky Way, which have a disk, and usually this disk has spiral arms in it. It has lots of features, lots of star formation. Inside, in the center of the disk, you might have a bulge, and then surrounding this, spiral galaxies often have halos of stars. So they're two very different types of galaxies. And then there's also galaxies that exist on all the scales between these two that you can imagine, and astronomers have given them names like lenticular, irregular, and so on and so on. And in fact, it's quite popular to categorize galaxies, and one very famous categorization, probably one of the first ones, is the Hubble sequence, Edwin Hubble came up with it, and he put galaxies along a tuning fork, so-called because it looks like a tuning fork, where he put elliptical galaxies at one end of the fork and then spiral galaxies at the other end. And then as galaxies kind of changed in shape, he gave them different letters and numbers and names, and people have kind of gone with it pretty focusedly and have given all kinds of galaxies lots of different names and letters, and they love to classify things. But the important thing is that there's two basic types, and people think that somehow the shape of galaxies is related to galactic formation. And originally, actually, Hubble thought that elliptical galaxies eventually formed into spiral galaxies. So it's kind of like an aging thing. As they got older, they would eventually flatten out into disks and become galaxies. But now we believe that that is wrong. And in fact, it might happen in the opposite direction, where spiral galaxies can eventually form elliptical galaxies. But to understand galaxy formation more, we really have to learn about dark matter. And so I'll begin an introduction to dark matter now. So for those of you who haven't heard it before, dark matter was kind of thought of in the early 1900s. And the first concrete evidence for it was found by Vera Rubin in the 1970s. And what she found was that stars in galaxies are traveling faster than they should be. And I want you to kind of understand that a little bit more, so I'm going to give you a crash course on orbits, and using our solar system as an example. So the sun and the Earth, and we all know the sun, the Earth travels in a circular orbit around the sun. And it has a very specific velocity or speed that allows it to travel in a circular orbit. But if the sun increased in mass suddenly, the Earth, if it kept the same speed, it would end up spiraling into the sun because it doesn't have enough energy to stay out of the gravitational field. So in order to stay in a circular orbit, it would have to increase its speed. So a good analogy to this is, well, a popular one at least, is the funnel analogy, where you say a gravitational field is similar to a funnel, like the ones that they used to have in malls where you flick a coin into them and then they spin around. So if you just drop the coin into the funnel in the mall, or if we just drop a planet into the gravitational field of the sun, it'll fall right in. It'll just fall into the sun, and your coin will just fall down the funnel into the bottom. But if you give the coin a flick, or if you give your planet a little bit of speed horizontally before letting it go, it can actually fall into a circular motion or an orbit. And then if you make the funnel steeper, or your star, the sun, more massive, your speed needs to increase. You need to flex that coin faster in order for it not to just fall down. So that's exactly kind of the analogy that I'm going to use here. And we can apply this to galaxies. So here, it's the same idea, where we have the speed of stars on their orbits, and we're looking at stars at different distances from the center. And then we can, using the opposite technique from what I just showed you, we can say, oh, if a star is going so fast in its orbit, there must be this much mass inside of its orbit. So if we take all the stars, all the mass that we see and count it out, we can decide exactly how fast each of these stars should be going. And you come up with a star near the center should be going about this fast, star out here should be going up that fast, star at the very edge should be going pretty slow. But then what we actually observe is that yes, this doesn't happen. And it follows that pretty well in the beginning, but then there's no turnover. And once you get outside the central portion of the galaxy, the star's speeds actually increase or stay flat in some cases. So stars have much higher speeds than they're supposed to have. So we're obviously missing something here. And astronomers came up with the idea that what we're missing is some matter, and we called it dark matter because we don't know what it is. And I wanted to show you that this is like, this cartoon I draw is shown in many papers. Like, this is actually what people observe. This is the same figure where we have speed along this axis and then distance along this axis. And they say that with just the stars, you should follow this curve. But then what they actually observe is all these data points. And what this paper did was they calculated the distance and decided that they were missing a whole bunch of mass, this halo. And we assign that to dark matter. And then we can calculate exactly how much mass that is. And as an example, in the Milky Way, first talking about stars, there's about 50 billion times the mass of the sun in stars in the Milky Way. So it's like 50 billion stars approximately. And there's about 700 billion times the mass of the sun in dark matter. So that's 90% dark matter of our galaxy. 90% of the matter in our galaxy is actually dark matter, which we don't understand. And this is actually a typical proportion between normal matter, where I mean stars and gas and regular stuff you can touch, versus dark matter. So what is it? Well, one of the things we know about it is that it appears to only interact through gravitational force. So it doesn't interact through the strong force, the weak force, the electromagnetic force. We can't touch it, we can't see it. It's only through gravity. So there's some ideas about what it could be. Like maybe there's like a bunch of planets out there, or maybe there's maybe they're some kind of weakly interacting massive particle, a WIMP. Or maybe there isn't dark matter, and instead our laws of gravity just don't work the same way on large scales. So a lot of astronomers have come up with ideas about modified gravity, like MOND, where at such large scales, you basically say our laws of gravitation don't work correctly, so we need some correction factors. But actually, in most circumstances, dark matter fits the evidence observations most closely. So that's what mainly most astronomers work with. So going back to galaxy formation and our ideas, to explore this further, since dark matter plays such an important role, what astronomers started doing was using simulations of dark matter to simulate how the universe evolves and how galaxies form. So this is a picture from one such simulation. And if you were here a couple months ago for George Stein's talk, he talked all about how cosmologists make these simulations. So because we can't, the reason we use these is because we can't actually observe galaxy formation happening, because it happens on timescales of billions of years. So whenever we observe a galaxy or galaxies, we're just observing them in a snapshot, a tiny snapshot of their lives. But if we can run these simulations, which run from the beginning, almost the beginning of the universe until present day, we can actually watch how the universe evolves. So this simulation, I haven't told you anything about it yet, is from the Millennium simulation, which is only run with dark matter particles, so only including gravity. And the size of this simulation is more than 1 billion light years across. So in all of these little yellow dots, those are where galaxies form. So this encompasses many, many galaxies. And I put some in there to show you where they would form. And the way, And we think that the whole universe is filled with this web-like structure of dark matter, which has been dubbed the cosmic web. And as I said, this is run with just dark matter. So we need to figure out a way to go between this simulation and what we actually observe. Because we don't observe dark matter, we observe stars and gas. And the way that we do this is we match up each of these little dark matter clumps with galaxies by size. So, for example, we take each of these dark matter clumps, and then we say, okay, this is a small clump, so let's match it with a small galaxy. And then we take like a medium-sized clump, and we say, okay, let's match that with a medium-sized galaxy. And then the largest size clumps we match with large galaxies. Make sense? Yeah. And I might slip into calling these dark matter clumps halos, because astronomers call them halos because dark matter doesn't condense into compact objects like gas does, because it doesn't interact except through gravity. So we've dubbed them, we call them halos because they're just kind of spherical. So if I say halo, I'm talking about the dark matter. But I'll try and just say clumps to make it more clear. And one thing, so carrying on, one thing we observe from these simulations is that the large clumps, the smaller clumps of dark matter actually merge together to form these larger clumps. It's a hierarchical formation of these dark matter halos, which in turn implies that the way that we form large galaxies is by merging together smaller ones to make the larger galaxies. And we actually see evidence for this in observations. And one example is that when we look at large galaxies near us, such as M101, we see that it's surrounded by smaller galaxies, which we call dwarf galaxies, which are satellites of the bigger galaxy. And that's evidence that these are accreting, that these could be accreting onto these larger galaxies. And we also see more evidence like streams of stars coming off from some galaxies indicating merging events and so on. So, but that's our general picture. And all of these galaxies seem to have some kind of regular ratio of dark matter to normal matter. About 90% of the matter in these galaxies, of the mass in these galaxies, is dark matter. So, is that it? Well, we still haven't figured out what dark matter is. So how do we figure that out? And because it doesn't interact except through gravity, we're having a very difficult time detecting it on Earth. And in the galaxies that we've observed so far, we don't see anything that argues convincingly against dark matter. But what if there was another parameter space that we could explore? And that brings me into this plot, which is a plot of brightness, but not just normal brightness, surface brightness. So surface brightness is just brightness divided by the area and against size. And I plotted someone's plotted galaxies on this plot. And the reason surface brightness works well for this plot is because galaxies aren't point sources, for one. So it makes sense to talk about brightness over an area. And also, surface brightness is independent of distance, unlike regular brightness. So we can plot all the galaxies on the same plot, no matter what distance they're at. And what you'll notice is that all these galaxies line up along this kind of linear line. And these are all types of galaxies. These are elliptical galaxies, spiral galaxies, dwarf galaxies. All those galaxies line up along this line. Above this line, we have small, bright, compact objects, which are stars. But then below this line, we don't detect anything regularly because the surface brightness is too low. But what's hiding there? Because right now it's our instrumentation limits that are causing us not to see anything. That doesn't mean anything is there. And why haven't we observed at low surface brightness? So this is an image taken of a star, Vega, by a regular reflecting telescope. And I just wanted to note that this is a normal image with the colors reversed though, so black means bright now and white means faint. And often astronomers reverse the colors like this because it's sometimes easier to see contrast. So this is a normal image. Just wanted to mention that because you'll see a few more in the talk. And the point is that these are not nice, pretty images of that star. They have some pretty serious effects going on, such as this huge halo aureole and these spikes. And the thing is that state-of-the-art telescopes all have these big diffraction effects. And if you're trying to observe something very faint and spread out, these really mess up your image for you. And this is a fundamental problem with the basic design choices that allow big telescopes to exist. And you can't solve this problem by making a bigger telescope or integrating for longer, because it requires eliminating systematics in your optical system. So where does this scatter light come from? So this is like a typical light train for a reflecting telescope. So the light, the skies would be over here, and the light would come in, and it would bounce off one mirror, which you call the primary mirror. It would be reflected to a secondary mirror, and then it would get sent off, reflected again to your camera or you. And as telescopes get bigger and bigger, this primary mirror gets bigger, but this secondary mirror also gets bigger, which means you have this big obstruction in front of the sky, which means you have lots of scattering. So obstructions are bad. And then the other thing is that for these big telescopes, they all have mirrors, and just tiny imperfections in mirror surface can cause these grain-like effects on your image, which ruins your image quality. So reflective surfaces are also bad. So what is the answer? Well, what we'd like to do is have a refracting telescope where we eliminate mirrors and obstructions. But there's a reason that astronomers have decided to use mirror telescopes, which is that we cannot really make lenses bigger than about 1 meter in size, because the lenses themselves just become flawed. It's just a technical problem of actually making the lenses themselves. So what can we do? We can't just make this very, very huge. That won't work. But what about using many smaller refracting telescopes? So even though we don't really use refracting telescopes anymore in astronomy, they are used very often in commercial applications, such as taking pictures with Canon lenses. And a prof at Yale, Peter Van Dockum, actually is an avid photographer, and he loves to photograph dragonflies. And he heard about these new lenses. He heard like 5 years ago, 5 years, I can count. Yeah, 5 years ago, about these new lenses that Canon were making, where they've made advances in the optical system that get rid of diffraction of light and reflection of light inside the lenses, to get rid of stuff like this, which you don't want inside your pretty pictures. And they also have made advances in coatings. So they recently just started making nanostructures to coat the lenses inside the Canon lens, which reduce reflections. So here's an example of that. On this right side, this lens has been coated with this anti-reflective coating, and on the left it hasn't. So all of these together made Peter say, I bet these new lenses with special coatings would be really good for astronomy. And here at U of T, Prof. Bob Abraham in the astronomy department was like, okay, sure, let's see how that goes. And then 4 years ago, that was the birth of Dragonfly. So Dragonfly started out with just one Canon lens. It soon grew to 3, 8, 10, and most of the science so far has been done with 10 lenses. And then recently it's grown to 48 lenses. So we have 2 of these mounts. So this is just half of Dragonfly right now. And it's in New Mexico. So we go visit it every year to check on it. So one half is here and one half is here. And it's actually just in an amateur astronomy observatory. And then, we take pictures. We have fun. But enough of my vacation pictures. Let's get to the science of what Dragonfly does. So, one of the first fields the Dragonfly observed was the Coma Cluster. So the Coma Cluster has been very well studied. It's about 300 million light years from us, and it's a cluster of galaxies, and it has many huge elliptical galaxies in it, and many other types of galaxies as well. And so we decided to just point Dragonfly at the cluster and see what it would find. And what it found was that Coma Cluster was filled with some kind of object. So each of these red boxes circles one of these faint objects that we found. And we called them ultra-diffuse galaxies, and they look like this. So in this middle column, we have some example Dragonfly images of these objects, and they're all extremely faint and extremely diffuse, which is why we call them ultra-diffuse. And then it turns out that you can also see them in other telescope data. So in the right column, we have data from the Canada, France, Hawaii telescope. And you can see that even though it's not as clear as in the Dragonfly image, you can see some fuzzy stuff there at the location of the objects in Dragonfly. And it's an interesting comparison because you can find them in there, but the thing is that if you see them in the CFHT data first, you don't know if they're real because of all the effects I've just talked about, the scattering of light and the imperfections. Whereas in Dragonfly, we are very confident they are real because you don't have any of those scattered lights. So getting back to this plot I showed you, well, it turns out that all of those galaxies we found fit right inside that area. So this is the same plot with surface brightness against size. And these are all the Coma objects that we found. And they all lie under that surface brightness limit. It's super cool. And then for comparison, we also show different galaxies. These are actually dwarf galaxies in the hollow circles, and then lots of large galaxies from other surveys. So it looks like we've opened up this whole new realm of galaxies and imaging. And we can do a comparison of the different types of galaxies. So this is Andromeda, our largest, closest neighbor, and also a spiral galaxy like the Milky Way. And then there's a dwarf elliptical galaxy here, and this is what the ultra-diffuse galaxy would look like compared to those two galaxies. So you can see it's something different. It's bigger than this dwarf galaxy, but fainter than Andromeda by a lot. So what is it? Is it just some kind of weird dwarf galaxy? Is it a disrupted galaxy, like perhaps a normal dwarf galaxy that got torn apart? Or is it some kind of failed Milky Way type galaxy that somehow didn't form stars? And this big question can be answered by looking at the mass of the galaxy, because going back to this dark matter clump or dark matter halo idea, remember the dark matter halos are matched to how big the galaxies are usually. So if it was a dwarf galaxy, it would have a small dark matter halo, whereas if it's a failed Milky Way type galaxy, it would have a large dark matter halo associated with it. So we really want to find out how much mass it has, or all of them have, because there's a bunch. But to start with, we only looked at one galaxy. So we picked out the brightest ultra-diffuse galaxy, which is Dragonfly 44. So it was over here, and this is what it looks like. And what we did was we used one of the largest telescopes on Earth, the Keck telescope, to find the distance to the galaxy. This is to answer the first, to either check or cross off the first type of galaxy, which is it a dwarf galaxy? Because if we find that it's much closer to us than the Coma Cluster, then it could be a much smaller object. It could be a normal dwarf galaxy. So how we measure distance is by looking at using the Doppler effect. So for those of you who aren't familiar with the Doppler effect, I have a GIF to show you how this works, and it works for both sound and light, is that if you have an object emitting, let's say, light, when it comes towards you, the light it's emitting ends up getting blue shifted, because you can imagine that these wavelengths of light are getting compressed. Whereas when it moves away from you, the light coming from that object becomes red shifted. I'm going to do it again. And this GIF also includes a spectrum, which is handy, because what happens is that you can look for features inside the spectrum, like lines, and you can see how they shift. And how much they shift depends on how fast that star is going. So what we did was we took a spectrum of DF44, and this is a picture of a spectrum. So you have wavelength on the x-axis and brightness on the other axis, and you just see how bright the light is at different wavelengths. And then we can look for features, and we find the velocity, and we found that the velocity of DF44 was consistent with it being inside the Coma Cluster. So it appears to be part of the cluster of galaxies, which means it would not be a dwarf galaxy that's close by. So we'd cross that one off. But is it a disrupted galaxy? Well, we can first just look at it, and it doesn't look like it. Just as a first, you can just look at things and decide. You can't quite decide, but you can get a feeling. It doesn't look like it's being tidally disrupted, because if it was, it would have some kind of irregularity, or things do when they're being tidally disrupted. But this looks very spherical, very smooth, whereas if something's being disrupted, it would have streams of stars coming off of it. And you might see a companion, which is disrupting it, because how this disruption happens is by gravity. So if another galaxy comes close by, it could tear off part of this galaxy and cause it to become expanded. But to do a more quantitative analysis of whether or not it's a failed Milky Way galaxy or disrupted galaxy, we're going to find its mass, like I said. So we took another study of this. Here's DF44 again. And this time, what we did was we looked at the velocities of things orbiting the galaxy. Just like in the example I gave about how you find out how much dark matter is inside a galaxy at the very beginning. But in this case, since the stars in the galaxy are so faint, we can't use them. But luckily, there were many clusters of stars, globular clusters, which are just groupings of stars that probably formed together inside DF44. So we measured the velocities of these clusters, and what we found was that there was lots of dark matter. In fact, even though there's 100 times less stars in this galaxy than are in the Milky Way, it has the same amount of dark matter that the Milky Way has. And a direct quote is, from the paper that this data was released from, is the more massive DF44 can be viewed as a failed Milky Way galaxy, which is pretty crazy. Because it seems to be a whole different type of galaxy that we discovered. So even though it has the same number of stars as a dwarf galaxy, it has a huge dark matter halo. So we're still trying to figure out what this means for galaxy formation, but one consequence is that the matching between the dark matter clumps and then the galaxies by size doesn't work in this case. So our whole idea of how we base our galaxy formation on that doesn't include these galaxies, and clearly it should if they exist. So what does this mean for the rest of the conclusions we draw from the simulations, and where does this fit in? But I guess before we take our conclusions too far, probably the most important question is how many of these types of galaxies are there? So is this the same for all of the ultra-diffuse galaxies that we've been finding? So the second galaxy I'm going to talk about is NGC 1052 DF2. Yes, which we just studied over the past year, and we believe it is associated with NGC 1052, and it was originally identified as a dwarf galaxy. But what we noticed was that if you compare the image in Dragonfly to its image from a different telescope, for the Sloan Digital Sky Survey, in the SDSS image, there's a whole bunch of clumps associated with this galaxy. It's not a smooth galaxy like the other dwarf galaxies are. So we thought that there might be something funny up with this galaxy. So we decided to take more Keck observations and Hubble Space Telescope observations to look at it more closely. So this is a Hubble picture of DF44, or NGC 1052 DF2. And you can see that it's very, very diffuse. And with the Keck data, we took spectra of all these compact objects and to determine their velocities. And what we found was that there were 10 objects with velocities that were similar to the group NGC 1052, and using those 10 globular clusters, we determined the mass. And what we found was that there's very little dark matter inside this galaxy. In fact, there's 400 times less dark matter than we would expect for a galaxy this size, and it's actually consistent with lacking dark matter completely. So this is almost the opposite case of DF44. And actually, something that's interesting about this is that this might actually be a nice piece of evidence for the existence of dark matter, which is kind of converse because it appears that there's no dark matter. But unlike modified gravity, you can't just turn off modified gravity for some galaxies and not for others, whereas with dark matter, you can just take it out of some galaxies. So it's kind of an interesting idea. So if we compare the two that I just talked about, NGC 1052 DF2 and DF44, they look so similar, but one has too little dark matter, 100 times, and one has 100 times too much dark matter. So until we start exploring more of these ultra-diffuse galaxies, we can only start thinking about the implications. But clearly, the way we assume dark matter halos are linked to certain galaxies may not be true. And this could lead to further understanding of star formation, like what caused it to turn off or to turn on in these galaxies, and interactions between galaxies. So we'll have to continue surveying more of these to find out more. But it looks like galaxy formation is not as clear as we thought. Not that it was ever very clear, And coming up is the Veneto galaxy survey. And this is a recently reduced image, which I've been working on for the past 6 months. And it's finally done, pretty much. And this is the biggest, longest dragonfly image. It's the first one from the whole 48 lens array. The other data was both of those other galaxies were just done with the 10 lens array. And it's equivalent to about 30 hours of imaging with Dragonfly. So it's going to be pretty cool. So keep your eyes peeled. And thank you very much for attention.
Okay, thank you very much, Deborah. That was great. So we have time for some questions. So I'll let Deborah pick, and we'll try to get a good spread around the room.
Yeah.
So you said that you cannot control gravity in the galaxies, but it's possible to have less or more dark matter. Why one is impossible, whereas the other is possible?
So the question was, why can you, if I'm understanding correctly, why can you not turn off modified gravity for some galaxies and not for others, whereas you can turn off the amount of dark matter? That's a great question. Well, I guess the difference is that if we look at modified gravity, what's happening there is that we're actually changing the laws of physics. And you can't just say that the laws only apply to some galaxies, whereas they don't apply to others. Whereas for dark matter, since it's just matter, that's easy to remove from galaxies through interactions or other events. So it's one of them, yeah, that's why.
So it's
Yeah.
a hypothesis or theory?
No, this is which one's a theory? Sorry?
Like your statement.
No, it's true.
It's proven, right?
Yeah, well, actually, for DF2, it was pointed out that there are certain cases for modified gravity where there's like a tidal effect, which can apply to NGC 1052 DF2, in which case it's slightly consistent with modified gravity. So there's like other laws and things, but yeah, this is true. Yes.
Just like, because you had the one galaxy I had, a lot of them have high amount of dark matter, others have virtually none. And then I think at the start you showed that web, that was kind of a distribution of it.
Mm-hmm.
Just have you noticed any sort of logic behind the distribution so far, or are we completely in the dark? Or,
The distribution of dark matter?
yeah, like do we understand or have any idea of like the pattern of the distribution?
So the question was, do we have any idea of the dark matter distribution? And do you mean like in the cosmic web?
Yeah, do we just have like any understanding behind how it forms, or are we looking at it and saying it looks like this? We don't.
Oh, yes. So we do understand how the cosmic web itself formed. So what happens is that if you start from the initial conditions, which are laid out by something called the cosmic microwave background, which is the first light in the universe, you can see that it actually has small underdensities and overdensities, which are related to the dark matter distribution. So if you just start the universe with dark matter in it, and then put in these little underdensities and overdensities, and then set it going, it forms into this cosmic web structure.
Okay, so it's more the distribution of the web with regards to dark matter than dark matter distribution with regards to something else.
Yes. Yes. Yes.
So I'm trying to make this three really quick ones. First, you mentioned something about how galaxies take billions of years to form.
Yes.
I could be wrong. I was kind of under the impression that they all already formed during the earlier parts of the universe. Second thing, I'm does dark matter interact with gravity exactly like normal matter does, or are there some weird differences? And third question, I promise I'll keep this quick. As much as we see a lot of galaxies in the universe, if we plot out where they are in relation to each other, does it look like, do the visible galaxies form a kind of web like where you described with dark matter was?
Yes. Okay, cool. I'm going to try and remember your questions. I'm going to start with the first one. Okay, the first one was galaxies. Didn't they form a long time ago?
Yeah.
Is that right? Yes. So most of the galaxy formation did happen at the beginning of the universe. But then this process of individual smaller galaxies merging into larger ones is actually still ongoing. So that because these objects are so large and they're on such long orbits, just the process of merging one orbit of one galaxy around another one could take 1 billion years. So it just takes forever. Okay, yours.
Does dark matter interact with gravity like normal matter?
So the question was, does dark matter interact with gravity? Does dark matter interact like normal matter does?
With gravity.
With gravity. Yes, yes. So yes, exactly. So for dark matter, we basically just assume that the only way it interacts is through gravity, and we give it the exact same rules that we give regular matter. There's a third question?
Do the galaxies you see in the universe, do they form a cosmic web like?
Yes. Yes. So the question was, do galaxies form in a cosmic web? And yes, they do actually. It's very, very cool. But if you plot out the positions of galaxies, because there's been huge surveys of the sky now where you can actually do this, and they do form a web-like structure. If you go to the planetarium show, you can see it at the very end, perhaps, if it's not in the show. It might not be in the show this time, but yes. Or which one? Yes. Yes, you.
Me?
Yeah.
All right, so 2 questions. One of them is dark matter. You talked about being dark matter, and then there's that plot about what's too dim to be seen.
Yes.
So far as the evidence pointing in favor of dark matter being just regular matter, but somehow not illuminated, or is it some sort of very exotic matter that just interacts gravitationally and cannot interact electromagnetically and with photon nonsense? And the other question is with the Dragonfly Telescope. If you're combining light from multiple scopes, is it actually going to be in a situation where it's creating other issues that don't play traditional?
Okay. So the first question was, I can remember. What was the first question?
Is evidence pointing in favor of being kind of basically regular matter, but not illuminated, or
Right.
exotic form of matter?
So the question was, what is dark matter probably going to end up being? And right now, as far as I know, the evidence is pointing towards some kind of exotic matter, such as WIMPs, weakly interacting massive particles. So astronomers have tested for the idea that it's some kind of like black holes, maybe floating around all over the place, but those have detectable observables, and that we haven't seen any of those. So.
And the other one is about the combining of light from that bundle of pulses.
Yeah, so the question was, are there other systematic effects that we're running into now that we're combining many, many images from all these different lenses? And the answer is we haven't run into any yet, which is exciting, yes. But it's actually one of the big strengths of Dragonfly is that because we're able to combine images from 48 different lenses, we reduce those systematic effects down so much.
So we'll just take 2 more questions with the whole
Which
room,
ones?
but Deborah will still be
Sorry.
around afterwards, so we'll just do 2 more.
Yes. Yes.
I realize this is sort of basic, but when you talk about measuring how much dark matter there is in these different galaxies, I assume you're doing it only by the gravitational effect. Is that right?
That-
Like even with Dragonfly.
Yes.
Dragonfly gives you better visuals, but it doesn't actually let you measure dark matter any other way than by gravitational effect.
Yes. Yes, that's right. So yeah, we're doing exactly the same thing that other telescopes are doing in order to detect dark matter. And actually, to make the mass calculations, we use other data. We don't use Dragonfly data. Dragonfly's mainly been just to actually find them and believe that they're real in the first place. Yes?
What is the dark matter difference between EF44 and normal galaxies like spirals, elliptical, and dwarfs? And what are some physical changes between them?
So the first question was, what's the dark matter difference between DF44 and other normal? So the difference is about 100 times different.
Okay.
Yeah.
And the second question was, what are the physical changes other than dark matter? Are there any?
So and the second question is, what are the physical differences between the ultra-diffuse galaxies and normal galaxies? And the main difference there seems to be they're very similar to dwarf galaxies, like spheroidal dwarf galaxies or ultra-faint dwarf galaxies, but just very diffuse and very large. So that's the main difference, is they're just huge, faint objects.